Next speaker will be Steve Muench from the Asprey Centre at the University of Leeds. And Steve, over to you.
Thank you very much, Tom, and thanks for the invite to come and speak today. So this is going to be a little bit different compared to some of the other talks. And if we've learned nothing else this morning and yesterday, I think there's a lot of different ways in making EM grids. And to some extent, what we need to consider is what the scientific question is that we're trying to address. So what I'm going to talk about today is something a little bit different and links back to sort of John's talk yesterday, and we're going to talk more about time-resolved electron microscopy. So if you're interested in a system that's going to make beautifully thin, consistent ice to get 1.5 angstrom structures, this might not quite be the talk for you, but it does hold some promise for other sort of areas of science. So what I want to do is just talk a little bit what is time-resolved EM, what is time-resolved studies, and we can go back to sort of the Muench work. Anyone who's seen the time-resolved talk has probably seen this example, so apologies for that, but it's a really nice example of what we're trying to do. So if we want to understand the molecular mechanism, in this case a horse running, the best way to do this, as Muench did in the 1800s, was simply to take a series of snapshots of a horse in action. Why do we do this? It's because it gives us two pieces of very valuable information. The first of which is we know the shutter speed, so we know the exact time point at which each of these events takes place. And that's very important. And the second is because this is on camera film, we know the order in which each of these time points takes place. And this is one challenge with in EM. You may start a reaction and you may be able to trap different conformational states, but how do you assign which state occurred before the other one, and how do you assign the time points between each one? And when we have all this valuable information, we can, of course, make these nice molecular movies, which we can then integrate with other biophysical techniques and biochemical analysis. And one of the big challenges with some of the systems we're looking at the moment is that, put simply, the reaction ends before we get a chance to study it. So with conventional approaches, we're looking at, in a vitro, about 8 seconds to make a grid. Most reactions have gone to completeness within 8 seconds. So how do we capture those intermediate steps before we reach the end point of the reaction? So what we need to do is to have a system whereby we can start to trigger a reaction and then stop it at distinct time points, or at least trap it in distinct time points, so that we can then study these in the electron microscope. So for clarity, what are the time resolutions that we're looking at? Well, we're not trying to compete with the XFEL beamline. The XFEL people are doing a brilliant job at doing femtosecond, picosecond time resolutions, looking at catalytic mechanism, looking at side chain motion. This is something that we're not delving into with time-resolved electron microscopy. Actually, time-resolved electron microscopy is very complementary to what they're doing in the XFEL beamline, because what we can do in time-resolved electron microscopy is we can look at large domain motions. So here we're talking about milliseconds, microsecond motions. Things like the ribosome in action, viruses decapsulating to release the cargo, for example. So all these lovely molecular machines that you can get in biology, we can start to trap them in different distinct states in the millisecond and hopefully the microsecond time frame, and hopefully to close to atomic resolution using the sort of EM tools available to us. So this is the area that we're looking at. So how do we go about this? So the strategy we've taken is not so kind in terms of sample usage, but it works for our needs. And this is a sort of an old system in a way. I mean, it goes back to sort of the acetylcholine esterase sort of experiments by Nigel Unwin, where we can take an EM grid, we can add our sample of choice, we can then blot it as we would do conventionally, and then we can pass it through a spray of substrate, in this case ATP, for example. This triggers a reaction, and the reaction is then stopped when it hits the liquid ethane. And our time delay of this experiment is from when the substrate hits the grid to when it gets plunged into liquid ethane. This can work very well. The issues here is in the mixing, particularly when you're using a small substrate such as ATP, and you don't quite know if it's landed on the grid or where it's landed on the grid, because you don't get distribution over the full surface of the grid. So another approach is to rapidly mix. So here we can mix the substrate and the protein together in a rapid mixing chamber. We can then spray them on a fast-moving EM grid that's then plunged in liquid ethane, and the reaction starts when you start the mixing, and then ends in the liquid ethane, and your time delay is this here. So this is good in terms of mixing, but hard in terms of getting the droplets on the grid so that you can get ice of the right thickness. And the third approach is to take a grid and add a caged substrate. So it might be a caged ATP, for example. You make the grid in a conventional way, and then you pass it through a light source that decages the compound, triggers a reaction, and then you plunge it in liquid ethane to stop the reaction. So on the outset of this project, we didn't really know which one was going to work best, so we thought we'd better make a machine that can, in principle, do all three, although at the moment we're focused primarily on A and B. So the first thing to say is that this has not been a quick process. And actually, in Leeds, there's been a history of sort of time-resolved studies, both in negative stain and cryo-EM for a number of years now. And Howard White, working with John Trinick, sort of initiated some of this, and these are some of their old systems. When I joined Leeds in around 2006, I started to use this system for a while, primarily making negative stain grids as well as cryo grids. And then with Howard White in around 2010, we started to make this new machine. And as you can see, oh, that's worked well. So what you can see is we're actually using the Vitrobot in this instance here to try and use the plunger and the ethane. So this worked with some success, but there was some significant limitations to this. So over the last sort of 2 years, we've designed a whole new system from scratch. We're again using John's principle of going to eBay and buying a lot of this stuff cheaply online. And if ever you want good fun, go to your finance department and get them to start a bidding war on eBay. It's amazing the resistance you get. So I thought it would have cheered them up in the office and given them something to do, but not so. But you can get remarkably cheap stuff from eBay, and we've now got quite good at understanding instructions for many different languages, and we can put these things together. So what we effectively have is a setup where we have the spraying nozzle here, and the mixing unit is right at the very end. We have some tweezers just at the top with the grid on. These are our blotting arms here. This box is a humidity chamber, so we can control the humidity, just to hope that the droplets don't absorb. We then have this system here of syringe drivers, so we can drive the protein up through the different sort of connections here into the sprayer. This is all operated by computer, so we can computer control the volumes at which we're extracting the protein. So it's all computer driven to give us some degree of repetition and consistency. And we plunge freeze it in a Vitrobot style container that's been slightly modified by snapping the middle. And then this here is the high voltage system that we introduced as well. So we actually apply a few thousand volts into the solution, and this helps to break up the spray. It's not quite a true electro spray, it's more voltage assisted spraying, but it actually gives us a finer dispersion of the spray, and it helps the droplets absorb onto the grid. And so what does this thing look like? Well, this is it in action. So this is on a loop. We obviously don't go up and down, that would be insane. But you can see roughly how quickly this goes. And then these are the syringe drivers here, dropping it through. And then this is our health and safety, a few thousand volt polystyrene box, which keeps us all safe from high voltage. So this is working quite well. We then got in touch with some of our very nice high-speed cameras, so we can start to look at these things in high speed, and we can look at it passing through the spray. And this is it going into the liquid ethane here. So we can use these videos quite nicely, because then we can start to accurately get an idea as to the speed at which these things are dropping down and passing the mixers. What do the grids look like? Well, I guess look away now to some extent, because they certainly don't look as pretty as some of the grids we've seen already today. And you get a lot of these very thick ice layers here, but you get these little islands of hope and these little regions of ice that you can go for. And this was one of those weeks that worked really well in science. For those PhD students and postdocs that are having a bit of a tough time at the moment, every now and then you suddenly get a breakthrough. And after many, many years working on this, we made some grids on a Monday, vapor ferritin, put them in the microscope, and we got some nice grids. And then when it was processed, it went down to about 3.5 angstroms. By no means as high as some of the other apoferritins that we've seen, but we didn't really try to push the resolution because we were so surprised we got a grid. We only had a few hours to collect the data. But just to check that this wasn't a one-off, we then thought we'd sling a ribosome in. We made some ribosome grids, and then we got some nice data to about 4.5 angstroms. Again, just from a quick overnight data collection. And one interesting thing is we saw a increased number of views of the ribosome compared to when we did this on sort of carbon-backed film, and I'll come back to that later on. We then wanted to see what happens to long, thin, sticky things, because it may be that the shear forces of this machine are making things rip apart. So we then put in some thin filaments, and what we saw is that we actually got really nice grids of thin filaments as well, and we can get a reconstruction down to sort of 5.5 of that, again using just an overnight data collection. And since then we've done a number of samples. I can't show you them all really, because some of them are quite sensitive in nature in terms of what we're working on, and others are. But we've also done things like proteoliposomes, which will be quite useful for later studies, we hope. We can add GFP-labeled protein, and then we can use the clone to try and identify it as well. So, of course, all I've shown you at the moment is that we can make grids that look a bit worse than the Vitrobot. That's not massively important. So what we want to do is to be able to rapidly mix things together. But the first thing we need to do is to be able to get some parameters together to work out how quickly we're mixing things. So very quickly, what we've been able to do is we can change the plunger speed. So this is reliant on a gas pressure. So we can go up to about 3 meters a second at the moment. Over in Hamburg, we got to use their high-speed cameras, and then we could measure the speed at which the droplets are going from the spray tip onto the grid, and we know that they start at about 5 meters a second and accelerate to 7 meters a second, so we can calculate the time of flight, if you like, of these droplets. And this then allows us to calculate time resolution. So in this experiment you're going to see here, what we're going to do is rapidly mix aperferritin and actin, and then pass it through the sprayer. We can do this with an approximate 10 millisecond delay, and then we can get grids we've got actin and aperferritin on them. We can then try a different approach whereby we take the grid, we put actin on the grid, and then we pass it through aperferritin, so we're going to blot, then spray. And again, this works as well. It doesn't work as well, but then that's no surprise, because you've already blotted the grid, so you've already got a certain ice thickness, and then you've sprayed on more solution, so you've just increased the ice thickness. And we've played around with this a little bit, but at the moment this is very much being parked to the side, because I think this is an approach that might be useful for some proteins, but we've got so many other things to do at the moment. We've not really taken this forward much more. But the capability is there if we do want to go back to it. But of course, at the moment, all we've shown is that we've been able to get two things on the grid. We don't actually know if they've mixed or not. This could simply be coalescence. They could be at different layers within the ice. So to sort of get around that, we tried a different experiment where we added actomycin S1, and we mixed this with ATP. And this has very well-established kinetics. And what we know is that after the addition of ATP, after 15 milliseconds, we expect 0, 10, 17, 99% dissociation of the mycin S1 in the presence of this volume of ATP, this concentration. And indeed, we see these furry fibrils here with no ATP. After 8 micromolar ATP, they remain quite furry, as we'd expect, with only 10% dissociation. But they start to thin out after 80 micromolar ATP, and after 800 micromolar ATP, we get these bare filaments. So it's not perfect. Some of the filaments are still slightly decorated, so the mixing isn't perfect yet, but it's pretty good, because a lot of the filaments that we see are all undecorated. So that shows that we are getting mixing, and we're getting it around the 15 millisecond time point at the moment. And for anyone interested in any more details, we've actually put this on the bioarchive at the moment, so if you want to know a bit more about this system and how it's set up, then please do check it out on bioarchive. I would add as well that we don't own any IP on this, we don't really intend to, so if anyone wants to make their own system, then there are designs out there. Please do come and visit us in Leeds if you want to see how you want to build one of these yourself. So again, using sort of John's philosophy, they're not cheap, but they're certainly cheaper than other systems out there, and you can buy a lot of this stuff off the shelf and then put them together and then develop them yourselves for other applications that you might want. So what I wanted to finish on was some of the more recent work that we've done that hasn't gone into the paper that some of you may have seen on the bioarchive. And what we've done now is we've switched to some different mixing units. So these mixing units were developed for the XFEL beamline over in Hamburg, although the group are now over in the States. And they've been making these really nice microfluidic devices for us that we've been able to put onto our system. So again, we've been able to take these nice pictures. You might be able to see here, the spray is actually slightly wider. Then again, you can see the jet. So if ever you wonder why your grid drops off in the ether, and you can see by the way that the tweezers sort of spring open as they land with the force. So what's nice about these is that we have a little bit more control as well in terms of generating jets and sprays. So if we have a low liquid flow pushing the protein through and a low backflow of gas, then we get jets, which we don't want, but we can then turn these jets into sprays. And what that looks like in real life is this. So this is a jet on the grid, and this is totally useless because what you've done is written a stripe of very thick ice across the center of your grid. But by simply increasing things like the liquid flow and the gas flow, or indeed putting the voltage on, what you can start to do is to spread out this jet, and then you start to get much more of these ice layers around the side of your grid. So we're now looking at sort of developing this further so we can get much more usable areas of the grid for these experiments. The other nice thing about this is that they go a lot quicker. So these droplets go at around 15 to 20 meters a second. Why is that important? Well, if you imagine that you're trying to do a time-resolved experiment, you can keep increasing the speed of the plunging arm, which is kind of useful, but not if your droplet speed doesn't increase, because at some point you're not going to get any droplets on the grid because you don't have enough droplets being dispensed. And so by going quicker in terms of the droplet speed, it means we can put much more droplets on the grid when we go quicker. So this means that we can now get down to time frames of around 6 milliseconds. 2 milliseconds is the fastest we can go at the moment, and that's limited purely by the speed at which we can move the plunging arm. So hopefully by the summer we can increase the speed of the plunging arm and we can go sub-millisecond into microsecond, being able to make these grids. Being able to make these grids is one thing, being able to make grids that are actually usable is another. And one of the biggest issues at the moment is that as the droplets land on the grid, you need time for them to spread out. And the quicker we go, the less time there is for these droplets to spread out. So there's a distinct correlation at the moment between ice thickness and speed, which we need to get around, because we can go faster and faster, but at the moment the ice is just getting thicker and thicker, and this is becoming a problem. So I wanted to finish on a few slides to go over a recurring point, and one that people have been asking me about this system, so I thought I will put it in now rather than wait for the question, and that's about the air-water interface problem. So, as has already been alluded to by the really nice work by Alex Noble and the Carragher group, they've shown that the faster you go, the more you can alleviate problems of the air-water interface. So it seemed sort of natural to see whether our system had a similar effect. So if you blot a grid, so in this case it's aperferritin because we've got freezers full of it, and you can see that it's pretty much all over the air-water interface. There's about 9% in the centre of the ice, but this 9% is probably there just because it's buried under the bodies of the aperferritin that's sort of degraded the air-water interface. So very little is in the centre of the ice. When we make a grid in 50 milliseconds, we see that we get a lot more in the centre of the ice. Note that the ice thickness is more, so we have 100 nanometers now rather than 60 nanometers. So we've increased the ice thickness, which will also affect the air-water interface interactions, but we do get a distinct additional sort of number of particles here in the centre. And actually, if we make a grid at 5 milliseconds, we see this feature carry on, but the problem is the ice is so thick it becomes harder then to do some of the tomographic analysis. So the quicker we go, the more we negate the air-water interface, but then we get problems with ice thickness. But what does this relate to in practical terms? So to look at that, we've gone to human HSP60. So this is a protein that was worked on by a member of the group as a rotation. And they struggled to get any useful, they got an okay reconstruction to about 7 angstroms, but they had significantly preferred orientation, and they could only really see the top views of this when they made it using the Vitrobot. If we spray the grids, we see that after 50 milliseconds we go from 7% side views to 15%, and after 6 milliseconds we get 19% side views. And this is probably quite conservative because this is based on the number of particles after a number of rounds of 2D classification. It's probably more significant than this. But the main take-home message is that when we make a Vitrobot grid from 800,000 particles that we can classify it down, or at least refine down to 125, we can't get any better than 7 angstroms resolution. Using a sprayed grid after 50 milliseconds, using significantly less particles, we get significantly higher resolution. And the only difference in this is the way in which we've made the grids. It's still not perfect. We'd still like to be higher than 5.5 angstrom resolution. We still probably need to collect a little bit more data, but we're still getting better than the 7 angstrom resolution that we're stuck at using the conventional Vitrobot approach because of the interactions with the air-water interface. So an added benefit of this system that we didn't really think about when we set out about this, and I think there's still a lot of work to be done by many other groups to look at the relationship between speed of grid preparation and the way in which you can negate the air-water interface. And so with that, just need to say that I think Timeresolved methodologies can allow us to trap states not seen through conventional approaches. And I think it's a really neat technique that EM can really dominate in terms of looking at these millisecond and microsecond different states, particularly because we're not confined by a crystal lattice. So that really helps in terms of looking at large macromolecular motions. And there's a number of large protein complexes that we can look at, burying themselves into membranes, transporting over membranes, all these sorts of systems that we can start to unlock using these techniques. There appears to be an advantage of making grids quickly, but this is still work in progress, very much so. It'd be interesting to see other systems and what their tomography looks like. And for some systems, I don't think it matters whether you're at the air-water interface. There's plenty of very beautiful 1.5 angstrom structures out there, 2 angstrom structures out there made on a Vitrobot. A lot of this is dependent on your sample. Some samples really like to be frozen, others don't. And this might be a means in which you can negate some of those problems. For us, many of the problems we need to overcome now is really in speeding up the droplet spreading on the grid so that we can get thinner ice. We've not yet used things like the wicking grids. This is something that we need to look into. And also changing the surface characteristic of the grids to improve their wicking capabilities. So this is something that we're also hopefully going to look into. A lot of it just depends on time and money and people. So probably the most important slide is this one here. So some big thanks. So Dimitrios worked on this project for just over a year. He's a materials scientist. So he brought an interesting outlook to the problem coming from a materials background on what we really don't understand about grid surfaces, etc. Very talented PhD student, David, who's got a poster. Please do talk to him. If you want to come to Leeds to use our system, then by all means get in touch. We're more than happy to take on new projects that we can try and test the system. And David's a very good one to go through. Find him at the poster. I'm sure he'll be very happy to make hundreds of grids for people. So he's a very talented PhD student who's worked on this for the last sort of year and a bit. Things I've not gone into actually is that we're actually working on mass spec as well and integrating this in other applications. In terms of the tomography, then that was primarily done by Becky and Molly, part of the cycling team as well. We're here, so thanks to them for doing all that. Hamburg, and now in America, Diana and Martin, who work on the XLB line, who've been really useful for mixers. Many of you may know Howard, who's been making these machines for a number of years now. Joachim Frank has a sort of an older generation which has sort of evolved down a slightly different stream, and that also sort of came from Howard's lab. So he makes a number of these machines, some of which are still lurking in UK laboratories around the place that we can update. So it's been great working with him for the last sort of 10 years, building these machines, particularly the last 2 years, because he's been taking sabbaticals in the UK. And the last mention is probably the most important one. So around 12 years ago, I came to Leeds because John Trinick offered me a job. So I had the opportunity of going to sunny California, and he convinced me to go to Leeds somehow to work on large protein complexes and macromecha machines. And he had a real sort of drive for understanding protein function. And he really built up the Timeresolved studies in the early days with Howard White. And it's through him that I really got into this area of science. So sadly, John passed away earlier this year. So this talk's very much dedicated to him, because without him, none of this really would have been possible. So thank you.
Thank you, Steve, for a lovely talk. We have time for a couple of questions. Dorian.
Hi, so you mentioned that it wasn't particularly sample friendly in terms of the quantity of material that you're spraying. I was just wondering if you could say for one run or stuff like that, how much material you're actually using up.
So we use a lot. So at the moment we generally use around 40 microlitres. So we've got a lot of dead volume which we're trying to reduce at the moment. So I didn't show you
this. Is that 40 microliters per grid?
It slows it, because once we've filled the lines, and actually you need less sample after that. So for one grid it's quite a lot, but then for subsequent grids it reduces. So it's just finding time and money to do this. So we've got a new system coming online next month, hopefully, which has a reduced line length, so that will reduce it down. The other thing you may have seen with the movies is we establish the spray for about a second before we drop the grid, and then the spray goes on for a second. So we do find people come with their precious protein and then cry a little bit when they see it being sprayed out into a plastic box, and then the grid goes down. So we can reduce that as well, because now we've got more parameters sorted out, we can probably reduce down those time lapse. So it's on our list to do, but we're never going to get down to this 1 microliter, nanoliter. That's a whole different experiment. I think those are fantastic systems, and we're not in that area at all. So time resolution, yes. Saving your precious sample, no, at the moment.
I was wondering about the if you've looked at absorption to carbon, because some particles will stick to the carbon, and if you increase the speed, does it decrease that sticking to the carbon problem?
Yes and no. We think there's something interesting going on, primarily because when we look at the tomography, we can see that one layer has a lot more protein than another layer does. And the layer that doesn't is the one that's on the carbon. So it may be that the carbon is absorbing so as the droplets land and then retract across, the carbon sucks up some of the protein, and that's why we get less on the bottom layer. So I suspect we are getting interactions with the carbon. How that relates to the time at which we do it, I have no idea, to be frank. We've just not done that experiment yet. It's something we need to do.
In these detergent protein samples, when you spray them, do you have problems of foaming?
We don't, which surprised us, because we also thought detergent would behave differently as well because of the surface tension properties. And actually we didn't find a massive difference between detergent and non-detergent. So, and also glycerol as well, we've been able to work with glycerol and big things and small things. So at the moment that's not been a problem. So I've not put them up, but we have sprayed a number of membrane proteins and they've been fine. So it doesn't seem to be a problem on our system.
Okay, I think probably in the interest of time we should close the session, but let's thank Steve and all the other speakers.